Hey folks, welcome to the video. In this video, we're going to be talking about the simple harmonic motion equation and complex exponentials. We all know the solutions to simple harmonic motion look like sines and cosines. They're trigonometric functions. These are closely related to complex exponentials, as we'll see today. Let's get into it.
We begin our exploration of simple harmonic motion with an explanation of complex exponentials. In particular, we look at the exponential e to the I t. E to the I t, given by Euler's formula, is cosine of t plus I sine of t. This is Euler's formula. A proof is linked in the description. Part of this formula, when t equals pi, gives e to the I pi equals cosine pi plus I sine pi. And sine pi is 0, cosine pi is -1, so this is -1. So an identity that we get is e to the I pi plus 1 equals 0. And this is Euler's identity. Euler's formula is particularly interesting because it is a combination of cosine and sine terms in the complex plane. Essentially, it's a wave in the complex plane. If we were to think about a circle of radius 1 in the complex plane, where this is the real axis and this is the imaginary axis, then the point corresponding to this on the circle can be found at t radians, where this point on the real axis is precisely cosine t, and this point on the imaginary axis is precisely I times sine t. Now, this is a great picture. The curve here, or the e to the I t expression here, represents this dot moving around in this circle in time, where time is essentially the angle between the horizontal real axis and the radial distance to the point. Okay, so why is this important? Why does it connect to simple harmonic motion? Well, let's take a look at the derivatives of the complex exponential. We can take the complex exponential, and in this case, let's actually multiply it by some value a times e to the I omega t, where omega here essentially tells us something about the speed at which this dot moves around the circle in the complex plane. So let's take a look at this particular complex exponential. We can write this as a cosine omega t plus I times a sine omega t. Now let's go ahead and differentiate this complex exponential with respect to time. Because a is a constant, we can factor it out. The chain rule gives us that this is equal to a I omega e to the I omega t. And let's differentiate once more. If we differentiate this once more, we're essentially differentiating this quantity here, which pulls down another I times omega, so we get I omega squared e to the I omega t. Now I omega squared is equal to I squared omega squared a e to the I omega t, and I squared is -1, so we get that this second derivative is -a squared e I to the omega t. Okay, so what does this mean? If we had some x of t, some function x, given by this complex exponential, then the second time derivative of x is given by negative omega squared a e to the I omega t. But a e to the I omega t is just x, so this is negative omega squared x. So d squared x by dt squared equals negative omega squared x. And this is precisely the equation for simple harmonic motion. Now notice that if x of t were equal to b e to the negative I omega t, then again d squared x by dt squared is equal to negative, well, in this case we would pull down two copies of negative I omega squared b e to the negative I omega t, and this is once more I squared times negative omega squared b e to the negative I omega t. I squared is negative 1, negative omega squared is just omega squared, so we get negative omega squared b e to the negative I omega t, and this is once again negative omega squared x. Okay, so we note that there are two complex exponential solutions over here to the simple harmonic motion equation. One with a positive I omega t and one with a negative I omega t. Because this is a linear ordinary differential equation, these solutions add. So x of t equals a e to the I omega t plus b e to the minus I omega t is a solution to the simple harmonic motion equation d squared x by dt squared equals negative omega squared x. Now, this is great. You might be more accustomed to seeing the solutions to simple harmonic motion in terms of cosines and sines. Now, recall Euler's formula. It relates the complex exponential to cosine and sine terms in the complex plane. We can turn this equation of motion, or we can turn the solutions over here, the complex exponential solutions, into these trigonometric solutions with cosine and sine terms as such. Suppose, so in this case, we suppose x at 0 is equal to x naught, and x dot, so the velocity at 0, is equal to v naught. Then we know that x of t equals a e to the I omega t plus b e to the minus I omega t is a solution to the SHM equation. So x of 0 in this case is a e to the 0, which is just 1, plus b e to the 0, which is again just 1. And this is x naught. Now x dot of 0. The a term gives us an I omega factored out times e to the I omega t. So we get I omega. A e to the I omega times 0 is just 1. And the second term, the b term, gives us a negative I omega times b e to the negative I omega times 0, which is just 1. So this is going to be equal to v naught. Okay, so from this step, what we do is we notice that dividing both sides by I omega gives us V naught over I omega is equal to A minus B. Okay, so we have two equations here, A plus B equals X naught and A minus B equals V naught over I omega. Okay, great. Now what do? Let's convert our complex exponential solution into one with sines and cosine terms. X of t is a e to the I omega t plus b e to the minus I omega t. We note that using Euler's formula, this gives us a cosine omega t plus I a sine omega t plus b cosine negative I or negative omega t plus I b sine of negative omega t. Because cosine is an even function, this is just cosine of omega t, and sine is an odd function, so this is sine. This is negative sine of omega t. Okay, so this is a cosine omega t plus I a sine omega t plus b I b. Oh, I'm sorry, there shouldn't be an I there. Sorry about that. Plus b cosine omega t minus ib sine omega t. Okay, so let's group the sine and the cosine terms together. So this gives us a plus b cosine omega t plus I times a minus b sine omega t. Now, we know from these two equations here relations between a plus b and x naught and a minus b and v naught over I omega. Because a plus b is x naught, this is just x naught cosine omega t plus I times v naught over I omega sine omega t. In this term, we have an I in both the numerator and denominator, so this is just v naught over omega. So we get x of t is x naught cosine omega t plus v naught over omega sine omega t. And we recover the usual cosine and sine solutions for the simple harmonic motion equation. Great. So let's apply this to a particular problem. Now that we know how it works in terms of complex exponentials and in terms of cosines and sines, we can apply this to a problem. Let's go with green. Or let's go with green. Okay. So let's apply this to a mass and spring system. Suppose we have a mass m that lies on a frictionless surface. It's just a block of mass m, and it's tied to a spring as such. The spring has a spring constant k, and the spring constant k determines how strong the spring is. If you were to pull the spring backwards and if you were to pull the spring and the spring has a low spring constant k, then the force it exerts to pull the block back is much lesser than the force it would exert if the spring constant k was higher. The equation of motion for this system is m times x double dot is equal to negative k times x, where x is the position of the spring, the position of the mass from the wall. X double dot here is the second time derivative. So written more explicitly, this is the equation of motion. Okay, now we can rearrange this equation by dividing both sides by the mass m to get this as negative k over m times x. Now notice the similarity between this equation and the simple harmonic motion equation as such. They are very similar in form, and in fact, we may set omega squared equal to k over m. So that means omega is the square root of k over m. Then we have d squared x by dt squared is equal to negative omega squared x, precisely the simple harmonic motion equation. If we suppose that our mass m starts at a value x naught and has initial velocity v naught, then its motion is given by this solution right here. So we may write x of t is equal to x naught cosine omega t plus v naught over omega sine omega t, where omega is the square root of k over m. And that describes a mass and spring system.
I hope you all found that interesting. Thanks for watching. Like, subscribe. I'll see you all next time.